All right, chapter 8, gases. So you may know that suction cups work by magic. Wait, no, they don't work by magic. So suction cups, if you put a suction cup up on a window, it stays there. You can often put weight on it. You can even hang plants on it. You can put a thermometer on it. You can do other fun things with suction cups. If you pull it off, after maybe some fighting with it or pulling the little tab that's designed to help you pull it off, and you feel the backside, it's not sticky, right? It's just normal plastic. So how does the suction cup stay up on the wall, on the ceiling? It turns out that the way that it sticks up is pressure. So we are right now surrounded by lots and lots of gas molecules. We can't see them, thankfully, so we can see each other, but we're surrounded by all of these gas molecules. And the suction cup stays up because it pushes out all the gas on one side, and it basically pretends to be part of the wall. And so all of these gas molecules are just pushed on one side of the suction cup, and it gets this net push force that holds it against the wall. It's literally just being pushed to the wall by air molecules. And the reason that they fall off so easily, especially if they're put on like a rough stone wall or like a stucco wall, is because they don't seal completely. So push only on, or push is only on one side when they're staying on. If you lift up, they have a little tab on it, that lets the molecules get behind it, and then it's pushing from the other side as well. Since air, being a gas, is fluid, it's liquid, it flows, it'll get behind it, and then it pushes from the other side of the suction cup, and that cancels out the force that was pushing it on the wall, which means that it's super easy to pull it off. This is sort of just for fun. However, kinetic molecular theory is not just for fun. It's also information for exams. So the kinetic molecular theory is what we're going to use in this class to understand the behavior of gases. Kinetic like motion, molecular like molecules. So we could also call this the moving molecules theory. Gas is made up of molecules, and those molecules are moving. This model works pretty well for predicting the behavior of gases under many conditions, including conditions that we're exposed to. Like a lot of other models, though, it's not perfect, and it will break down under certain conditions. We're going to focus on where it works well. It's also a relatively easy theory, which is part of why we're using it. We avoid some of the nitty and the gritty, including the dance. So the kinetic molecular theory has 5 points. It used to have 4 points when I taught it previously. That's not because they updated it, that's just because I changed the slides. So 1, our gas consists of many tiny particles in constant motion. That's kind of the name, the kinetic molecular theory. We've got little particles and they're moving around. Those gas particle collisions, there's so many of them, they have to run into each other at some point, are elastic. This just means that no energy is lost. So we're making the assumption, that's not entirely true, that when two particles collide with each other, they're like the perfect bouncy balls, they just bounce off. So if you had a perfect bouncy ball and you dropped it, it would bounce off the ground and it would come right back up to the same exact height, assuming you were in a vacuum and all these other things, right? So that's what we're assuming here. They're bouncing, they're not losing energy, they just bounce off. We're also making an assumption that they're separated by large distances relative to their size. So they're not actually separated by what we would consider large distances, but because the molecules, the particles are so small, large is also really small, these large distances. Basically what we're saying is there's empty space. empty space between particles. We're letting the gas be a gas. We're also making the assumption, which is wrong, that the gas particles don't attract or repel each other. This is technically wrong, but not to the extent that it's like significant. So they're not going to get close to each other and then slow down because they're negatively charged, and so they just don't want anything to do with each other. Nope, they're billiards balls, they're pool balls. They hit and they bounce off. They're not like one's got Velcro on it and the other's got the other part of the Velcro and they hit and they stick. They're not doing that either. They hit and they bounce off. And the speed of the particles depends, at least in part, on temperature. Higher temperature, faster particles. And that, I think, is always true. So those are our 5 big points for kinetic molecular theory. You should know them. So you can maybe revisit those during your studying. Make sure that you have those down. Kinetic molecular theory is consistent with some of the properties of gases. Gases are compressible. If you take like a plastic water bottle, or a basketball, you can squeeze it. And the surface of the ball will deflect inward a little bit, right? Because the ball has air in it. Soccer balls, volleyballs, lots of other balls, not baseballs, also that way. Right? You can compress them a little bit or a lot of it, depending on how pressurized they are. Tires are also compressible. Anything that's got a gas in it, you can compress that gas. So you can squeeze those particles down into a smaller space. There's a lot of empty space in there that lets you squeeze them together. Gases will also assume the shape of their container. So in a container, the molecules are not going to crash into each other and then form into liquid at the bottom. They'll crash into each other and they'll bounce off of each other. So they'll take up the entire space of the container. This is something that you would experience if you were on a road trip and one person had gas or Taco Bell or some other food, right? Their little aromas that they're making or enjoying will eventually make their way up to you, the driver in this situation, or other passengers. Or if it's like on a bus, eventually some of those smells will make their way out to other people, assuming the windows aren't open. Or if somebody was enjoying a particularly odorous serving of maybe fish in the classroom, that would eventually waft its way over to the rest of the people in the class. Those gases will move around and distribute throughout the room. Or when somebody's cooking, like if my wife is cooking at home and there's garlic or there's ginger, usually garlic, in the dish, eventually the garlic smells make their way over to me, usually at my desk in my office. And they smell delicious, and I come out and, oh, dinner's cooking. Love it. Gases also have low density in comparison to solids and liquids because there's a lot of empty space. There's a surprising amount of empty space between the gas particles. So a typical can of soda is about 0.355 liters. It's about a third of a liter. It's about 12 ounces. If you turn that into a gas, it would have a volume of 477 liters, which is about 2 bathtubs. So if you took that little can of soda, turned it into a gas, it would fill up 2 bathtubs with how much it expands. So if the particles themselves take up 0.355 liters, and the whole thing is expanded to 477 liters, there's 476.6 liters of just empty space between those gas particles. So that's a lot of empty space. It's mostly empty space. Okay, so some important things that we can build out of our kinetic molecular theory. Pressure, what we experience as pressure, is a prediction of our kinetic molecular theory. Pressure is the result of constant collisions between particles and surfaces. So there's lots of particles bouncing around. They are constantly running into us. These particles are extremely small, but there's billions upon billions upon billions upon billions upon billions upon billions. We're somewhere in that neighborhood. There's Avogadro's numbers of gas particles, and all of those tiny little collisions add up. They add up to a lot compared to the individual collisions. Pressure lets us do things like drink from straws. You can't drink from a straw in a vacuum. It doesn't work. We can inflate basketballs. So a lot of sports are possible because of pressure. Cars are possible because of pressure. You wouldn't have the tires without pressure. And we can also breathe because of pressure. Variation in pressure in our atmosphere also creates wind, and it helps predict weather by looking at changes in pressure. It's not actually trees sneezing like Calvin and Hobbes might lead you to believe. So pressure is a lot of little collisions. The pressure is defined as force per unit area. So a certain amount of force applied over a certain amount of area. Pressure depends on a bunch of things, including the number of gas particles in a given volume. So we've got two identical volumes. One of them only has a few particles, or relatively few particles. The other one has a lot more particles. The one with more particles is going to have more collisions. Because it has more collisions, it's going to have higher pressure. An example of a unit of force might be what? Who knows a unit of force? Huh? Newtons is a unit of force. Yeah, so, sorry, a unit of pressure. Did I say unit of force? Unit of pressure. PSI. What does PSI stand for? It's pounds per square inch. That's the one that I would expect most of us to be familiar with. Pounds is a unit of force. A square inch is a unit of area. PSI is an example of a unit of pressure. It's a little bit more explicitly force per unit area than a lot of other units. Other examples of things related to pressure. Some of these things are things that you should know. So pressure is lower at higher elevation. High elevation has lower pressure. This has a lot of important things related to it. The gases chapter has some of the most fun applications or the most relevant applications. So if you've ever been up into the mountains, hopefully you've been up into the mountains, that's at a higher elevation, you may find yourself getting winded more quickly. That's because of the decreased pressure. The decreased pressure means that there's less oxygen in the air, means that it's harder for you to get the oxygen that your body needs, so you feel winded sooner. You would also have probably experienced, as you were driving up to the mountains, your ears feeling a little bit weird, you not being able to hear super well, until you yawn or you're chewing gum or you do some other trick to get your ears to balance. So if you do that, go up into the mountains, there's lower pressure. As you're coming back down into the valley, you'll experience the same thing, but the opposite effect. So your ears have a little cavity inside of them, full of gas. And when you're up in the mountains and that normalizes, you'll have low pressure in your ears. You come back down into the valley, and the pressure starts to increase as you're coming down the mountain. And you'll feel a pressure forcing its way in, pushing on your ears, which is painful. If you're going up into the mountains, it's a higher pressure inside. It forces your eardrums to bulge outward, and that can become painful. This is why babies cry on planes. Not the only reason. Babies cry for lots of reasons, but small children and babies will often cry on planes because of that pressure imbalance. It's not their fault. They're experiencing pain, and they don't know what it is. They don't know how to deal with it. You can't give babies gum. You're not supposed to, at least, because it's a choking hazard. So they can't chew on the gum to get rid of the painful sensations in their ears, so they cry. So that's also something that comes out of pressure imbalances. For pressure, we have a bunch of other units, not just PSI. The simplest one, the one that may end up being your favorite, is the atmosphere. The atmosphere is the average pressure at sea level. One atmosphere is the pressure that you are experiencing on average when you are at sea level. So if you're at the beach, pressure right around 1 atmosphere. We are not much higher than sea level. We're like 400 feet above sea level maybe. And so our pressure is pretty close to 1 atmosphere. The SI, or the metric unit of pressure, is the Pascal. So there's another unit of pressure. It's defined as 1 Newton per square meter. A Newton is a small amount of force, at least compared to a pound. A square meter is a large area, at least compared to a square inch. So 1 Pascal is 1 Newton per meter squared. The Pascal is a much smaller unit than the atmosphere. There's 101,325 pascals in 1 atmosphere. For comparison with PSI, 14.7 PSI is the same as 1 atmosphere. Because a square inch is a relatively small area compared to a meter. A pound is a relatively large unit of force compared to a Newton. Do we have any questions so far? These unit conversions should be on your yellow sheet, so don't feel like you need to write them down. The important takeaway from this slide is that the atmosphere is the pressure at sea level. Another pressure unit that we have is the millimeter of mercury. Millimeters having the symbol mm, and mercury being Hg, hygrogram, or whatever it is. The mmHg originates with how pressure used to be measured. So the way that pressure used to be measured is they would take a really long glass tube. Take a really long glass tube and you would submerge it, fill it up with mercury. So you'd have to have a lot of mercury and you would have to have a long glass tube. And then you pull that glass tube out of the bath of mercury with the closed end down in the mercury. Eventually you pull it up high enough that the mercury stops floating. It stops coming up all the way. It'll only go to a certain height. And that height is equal to the pressure that's pushing down on the mercury. So there's pressure on the outside pushing down on the mercury, forcing it to go up into the tube. That height is the pressure outside. So this is how pressure used to be measured. The average atmospheric pressure at sea level pushes a column of mercury up to a height of 760 millimeters. So you'll see usually 760 mmHg equals 1 atmosphere, for example. You don't need to write that down. Another thing that I think is really fun that comes out of this is that this is literally, we're measuring a unit of length for a column of mercury. Since we're measuring a unit of length in millimeters, you can convert millimeters to inches, and it'll give you your value for inches mercury. So if you look at a conversion table, you'll see 760 millimeters of mercury. You'll also see 29.92 inches of mercury. 29.92 inches is about 760 millimeters. So I think that's fun. Any guesses on why we use mercury instead of water? How dense is mercury? Is it more dense or less dense than water? It's way more dense. It's liquid metal. Mercury is way more dense than liquid water. If you were to do this with water, instead of 29.92 inches, so a little less than 3 feet, instead of a little less than 3 feet, you would end up with a column of water that's about 32 feet tall. You wouldn't be able to do this with water because you probably don't have a 33-foot glass tube. And if you do, you probably don't have room to put it up anywhere. So the reason that mercury is used is because it's really dense and it's a liquid. All right, some pressure units. We've got a summary of a bunch of pressure units here. We've got pascals, that's our SI unit. We've got atmospheres. These are all the air pressure at sea level. So at sea level, 1 atmosphere. That's how it's defined. We've got our millimeter of mercury, our inches of mercury. We also have torr. Torr equals millimeters mercury. They are exactly the same, 1 for 1. We also have PSI, the pressure unit that we probably use when we're filling up our bike or our ball or our tires. And by bike, of course, our bike tires, tubes. Some conversions that you might want to memorize. 1 atmosphere is 760 millimeters mercury. Torr equals millimeters mercury. That's probably the most important one. And as I mentioned previously, you can convert from millimeters mercury to inches mercury the same way you'd convert from millimeters to inches. So in a pinch, if you know your centimeters to inches, you can figure out your millimeters to inches. You can figure out inches mercury to millimeters mercury. I don't know why you would be in that pinch, but it could happen. It also just saves you using Google. Or if you're like in the mountains and you're just curious. All right, let's do some examples. Let's try doing some unit conversions. We want to convert 1.25 atmospheres to torr. It's been a little bit since we've done some conversions. So we want to make a conversion factor between atmospheres and torrs. All of these values in this table are equal to each other, because this is the air pressure at sea level. So we find atmospheres and we find torrs. 1 atmosphere is equal to 760 torr. So 1 ATM equals 760 torr. We're going from atmospheres to torr. To make a conversion factor out of this, we can divide both sides by one thing. I'm going to divide by the atmospheres. The left side turns into 1. So our conversion factor is 760 torr over 1 atmosphere. I chose to do it that way because that's the fastest way. We'll end up canceling out atmospheres if we can't multiply these. The other way you could do it is just put one of them on top, the other on the bottom. That also works. We need the atmospheres on the bottom so that we've got one on top, one on bottom. Those will cancel. And we're left with units of torr. And then it's a simple matter of putting it into our calculator. 1.25 times 760, 950 dot torr. The dot there, so we have 3 significant figures. Questions? Go ahead and try the inches to millimeters conversion. All right, give you about a minute. We want to do a conversion from 30.15 inches mercury to millimeters mercury. Our conversion factor, we're going to find millimeters mercury and inches mercury. The one that we're going to goes on top, so 760 millimeters mercury. And the one that we're getting rid of goes on the bottom, 29.92 inches mercury. The inches mercury cancel out. And we're doing 30.15 times 760 divided by 29.92. So our answer is 765.8 millimeters mercury. The other way we could have done this is just converting the inches part. 1 inch equals 25.4 millimeters, which is exact. So multiply by 25.4 millimeters over 1 inch. The inches cancel. And we get 765.81 is what the calculator says. We would round it for 4 significant figures. So 765.8. It's the same number. I think that's just like a cheeky way of doing the problem, which is fun. All right. We already did it. I had you do the other one. We'll get into our first law, and then we'll stop after our first law. So we are going to learn some basic laws, some basic equations that are named on, I think, exclusively old, dead, white men. So Boyle is the first one that we're going to learn. Boyle's law relates pressure and volume. The pressure of a gas sample depends, at least in part, on volume. Pressure depends on volume. If the temperature and the amount of gas are constant, meaning you don't increase the temperature, you don't decrease the temperature, you don't add gas, you don't remove gas, then the pressure increases. Pressure increases when volume decreases. And the pressure decreases if the volume increases. This is a very, it's not actually that fancy way, but this is a way of putting into words what happens when you squeeze a balloon or a ball and then you let go. When you squeeze it, you're decreasing the volume. That causes the pressure to go up. The more that you try to squeeze a ball or a balloon or a water bottle, the more that you try to squeeze it, the further you try to squeeze it, the harder it gets to do that, because you're decreasing the volume, so the pressure is increasing, so you're increasing the force that you're pushing against. And as you release it, the force that it pushes out with also decreases because the volume is increasing. You're letting it relax back to its full size. That's all this law is talking about. If you squeeze something, the pressure goes up. This applies also to bike tires and pumps. So a gas pump, or a bike pump, or a ball pump, works in that when you pull up the handle, there's a little one-way valve somewhere in the body of that pump that lets air in. So you're pulling in air from the outside, and when you push down, you're compressing the gas that's in the shaft of the cylinder. You're compressing that, and it has nowhere else to go except through the tube and into the tire. And then you pull up, and it lets more air in, and then you push down, and then it pushes more air into the tire. And what happens over time as you're filling up the tire? Obviously, the tire inflates. Hopefully, it doesn't explode. It also gets harder to push down as you keep going because you're increasing the pressure in the tire, so the pressure that you're pushing against when you're pushing down on the handle also increases. So bike pumps work on this principle. So this relationship was at least noted by Robert Boyle, who lived during these times. I generally don't care about what their name was and where they lived and all that. It's not a history class. But it is named after Boyle, so we usually call it Boyle's law. So Boyle's law assumes constant temperature and constant number of gas particles. Boyle's law states the volume of a gas and its pressure are inversely proportional. When one goes up, the other goes down. That's the inverse part. Put another way, in math speak, volume is proportional to the inverse of pressure. This fish-looking half infinity, 3/4 infinity means is proportional to. And 1/p is also called the inverse of pressure, or inverse of p. The law that we get out of this, the part that we probably care about, is P1V1 equals P2V2. The ones here referring to state 1, so just one particular instance, one set of conditions, and the 2s referring to state 2, aka a different pressure and volume. The way that we get this P1V1 equals P2V2 from V is proportional to the inverse of P. Proportional to means that there's some constant. So V is equal to some constant, we don't know what the constant is, times 1/p. If you multiply both sides by P, you don't need to know how to do this, by the way. It's just for those of you that care or are interested. We would end up with PV equals K, some constant. Since that K is constant, it's always going to be the same. So we could say that this is equal to some other set of P and V. If we call them P1, V1, and P2, V2, and we just ignore the K in the middle, that gives us this P1, V1 equals P2, V2. That's our Boyle's law. So the original experiments, I think the original experiments for this were that adding mercury to this like hooked J tube, there's actually some air in here. It's just obnoxiously about the same color as the mercury. So with some air in here, there's a height of mercury that gives you that volume. If you add in more mercury, that adds more pressure because it's pushing down and it compresses this gas. If you add more mercury, it compresses the gas even more. Adding mercury increases pressure, so the gas shrinks. And if we plot this, if we graph it, the graph that we have here is a graph of Boyle's data. We've got volume on the x-axis. So from left to right, we're increasing the volume. And we've got pressure on the y-axis. So from bottom to top, we're increasing pressure. So at really high pressure, we've got really low volume. At really high volume, we've got low pressure. At low pressure, we've got high volume. However you want to think about it. This is not a particularly nice looking graph. It's got a shape to it. But it's much more helpful if we plot it with 1 over pressure. So inverse pressure on our y-axis instead of pressure. And we keep volume on our x-axis. And now, look at that. It's a straight line. Straight lines are a little bit nicer than curved lines for equations. That means that we've got a linear relationship between the inverse of pressure and volume. Kinetic molecular theory can explain part of Boyle's law. So if the volume decreases, if we move the lid of this container down, and we have the same number of gas particles in there, there's going to be more collisions because they have less space to move around. So decreasing the space, they're going to bounce more, they're going to hit more, there's more collisions. More collisions means more pressure. The way that we will often use these laws is in examples like this, and we'll end after this slide. So Boyle's law, P1 V1 equals P2 V2. A sample of gas has an initial pressure of 2.44 atmospheres and an initial volume of 4.01 liters. Its pressure changes to 1.93 atmospheres. What is the new volume if temperature and amount are kept constant? The place that you are most likely to mess up on these problems is either the algebra. Hopefully it's not the algebra though. The other place is getting your variables confused. It's important that P1 and V1 stay together. If you identify them incorrectly, then you'll end up with your variables mixed and you'll end up with the wrong answer. And I will have predicted it on the exam. So if you mess up, you might not notice it. So be very careful. We've got some pressures. We've got some A volume. So we've got a pressure of 2.44 atmospheres. We've got a volume given to us of 4.01 liters. We've got another pressure of 1.93 atmospheres. This volume goes with one of our two pressures. If you put it with the other one, you will get the wrong answer. Which pressure does the volume go with? Does it go with the top pressure, the bottom pressure? Which one do we pair it with? There is a correct answer here. The volume goes with the top pressure, this 2.44 atmospheres. Typically, I'm guessing, we would call this state 1, P1 and V1. Technically, it doesn't matter. You can call them P2 and V2. The way that we know that they're together is that 2.44 atmospheres is our initial pressure, and the volume is described as our initial volume. And so those numbers have to go together. We want to find what's the new volume. So we would call this V2 because it's our other state, our other set of pressure and volume. So using our equation, P1 V1 equals P2 V2, we're trying to find V2 to solve for something in algebra. We get that by itself. So we want V2 on the top and by itself. To move from P1 V1 equals P2 V2 to having V2 by itself, we need to divide both sides by P2. So P2 cancels on the right side. V2 is now by itself. The shortcut just moves something from the top to the bottom on the other side, or from the bottom on one side to the top on the other. So flipping that left to right, V2 equals P1 V1 over P2. Let's plug in our numbers. So P1 is 2.44 atmospheres. V1, we're multiplying 4.01 liters. And this is divided by 1.93 atmospheres. What units will we be left with? Liters. The atmospheres cancel. The atmospheres only cancel because they are both in atmospheres. If you're given one pressure unit that's in atmospheres and another that's in torr, you would need to convert them to both be the same pressure. Otherwise, the units won't cancel. So into our calculator, we're putting 2.44 times 4.01 divided by 1.93. And we get a number, 5.0 rounded up to 7 liters. That is our new volume. Questions about doing that problem? A way that we could check our work is the pressure is going down. What would cause the pressure to decrease in terms of volume? Would the volume get bigger? Is that going to decrease pressure? Or would the volume get smaller? Would that decrease pressure? Think about what happens when you squeeze a ball. When you squeeze a ball, you're decreasing the volume, you're increasing the pressure. This is the opposite. We're increasing the volume, so we're decreasing the pressure. So increasing volume makes sense. We will pick up here tomorrow.